Okay, good morning, everyone. Today I want to finish up mesh current analysis, the theory, the steps, and then the example problem. And then next class on Friday, we'll look at superposition. So let's jump in right away and bring up mesh current analysis. Selection 3. Okay, brief recap. Mesh current analysis uses KVL to generate equations. KVL means we are summing up voltages around a loop. In this case, the loop is a mesh, which is a simple loop, does not contain any other meshes inside it. Those mesh currents are hypothetical. They are not real. At the beginning of the analysis, the first step is to identify all the meshes, assume a current direction, and assign mesh currents to each and every loop. And so in this example, we have 3 meshes, 1, 2, and 3, M1, M2, M3. The mesh currents assigned are in the clockwise direction. It keeps things simple. And then the labels are I1, I2, and I3. We applied KVL to each mesh in sequence. For mesh 1, we have 3 components. Hence, we'll have 3 voltages and 3 terms in our equation. So we have VA, VR2, and VR3. VA is a voltage source. VR2 and R3 are the voltage drops across the resistors. So then we can apply Ohm's law and express each resistor voltage in terms of the mesh current. So similar to node voltage analysis, but here we are summing up voltages. In mesh node voltage analysis, we would apply KCL and sum up the currents. So exactly the same procedure. Okay, KVL you apply with any technique that you're comfortable with. I typically sum up the voltages in a clockwise direction. So my summing voltages in the same direction as the chosen direction for the mesh current. Hence, the voltages would be positive. When I go clockwise around the loop, I have VA as negative. I have VR2 and VR3 as positive. We have to account for both the mesh currents if the resistor is in a shared branch. R2 and R3 are in a shared branch. Shared branches mean the current for that mesh, which is I1, is positive. The current that is outside the mesh, I3, is negative. And same thing for VR2, I1 is positive and I2 is negative. And so, sorry, VR3. So it's I1 minus I2 times R3. And then here it's I1 minus I3 times R2. Okay, that's the quick recap. Any questions? The shared branch concept is that's the concept where most students trip up. There's a logical reasoning behind why it's I1 minus I2 and I1 minus I3. Okay, and that was shown here. Actually, that's shown right here. If you have a shared branch and all of your currents are going in the clockwise direction, it will always have one current positive and the outside current as negative. Okay. Let's say you choose one current going in the clockwise direction and the other current going in the counterclockwise direction. In that particular shared branch, let's take I1 and I3. Yes. Sure. So the question being asked is, why do we have positive, negative, and 2 voltage polarities on the opposite side of the same resistor? The answer is they are not real. Okay, they are not real. Those are voltage polarities that occur due to the hypothetical mesh currents. So the 2 voltages that are shown on either side of that resistor, which is right here, they are also not real. So let's take a look at R3, right? We have R3 up top. The voltage drop, the hypothetical voltage that would appear across R3 due to the hypothetical mesh current I2, or sorry, I1 would have a plus at the top and minus at the bottom. Make sense? Right? Point of entry is always positive, point of exit is negative. Then similarly, when we have to account for the mesh current on the other side, which is I2, it'll cause another hypothetical drop, which is plus at the bottom, minus on the right. So those two currents, again, those mesh currents are not real. So we can illustrate the two voltage drops with having two opposite polarities. Does that make sense to everyone? Okay. The mesh currents are not real, so the voltages that appear across the resistor are also not real. For the purposes of analysis, we assume a direction for the mesh current. We are saying we have two mesh currents flowing in the exact same resistor, which is not possible. Okay. And so two voltage polarities, both in the opposite direction. So when you add up the voltages, you would get I1 minus I3. And that brings me to the point. If we choose our mesh current in the opposite direction, meaning let's stick with R3, and this time my I1 is clockwise. However, I3, I'm going to choose, was it I3? I2. I'm getting confused between those two. And I2 is now counterclockwise. What happens then? You add up because both voltages are now positive. So you have a double positive. So now we pause plus here, minus here, plus minus here. So in M1, if I was to add this in M1, it would be I1 plus I2 times R3. What happens when I get to mesh 2? Mesh 2 is here. If my I2 was opposite, what would be the voltage drop? And that's why it doesn't matter what direction you assume for your mesh currents. If you choose, in the last example, the last illustration, one clockwise, the other counterclockwise, then in one mesh, you have double positives. Both mesh currents will be positives, but when you get to the second mesh, now you have double negatives. So it'll be minus I1 minus I3. It balances out. All right, think on that. Let me know if you have any questions. Does that make sense on why it's I1 minus I3 and I1 minus I2, right? So then mesh 2 was the same concept. We had R3 again that is shared. Same resistor from mesh 1. In mesh 1, we had I1 minus I2. But in mesh 2, we have I2 minus I1. Okay, the exact same resistor, the exact same voltage drop. VR3 is I1 minus I2 in mesh 1, and it's I2 minus I1 in mesh 2. Look at both the circuits, look at both the equations. Let me know if you have questions. Does that make sense? Hopefully. All good? Okay, moving on. Let's look at example. Three steps. First thing is identify the meshes, assign mesh currents, assume a direction, clockwise, counterclockwise, doesn't matter. I always suggest choose clockwise for all currents. That way it keeps things simple. Then you apply KVL to each mesh. All you're doing is you're summing up the voltages. You sum up the voltages with the technique that you're comfortable with. Write out all of the voltages before you apply Ohm's law. Okay, do not skip that step. So do not skip that step. Similar to node voltage, I say write out the KCL expression along with the current direction, because that's the most important step. And when students skip that one, they have the KCL expression incorrect. So here you write out the voltages first, then you apply Ohm's law and express each voltage in the mesh in terms of the mesh currents. Let me ask, how many of you do not have access to the class notebook or have not signed up yet? Class notebook? How many of you are on the class notebook? Okay, almost all of you. Okay, that's good. Just making sure. Okay, example. MCA, mesh current analysis. Problem is asking us, the problem statement is solve for all mesh currents and the resistor voltages. There are 3 voltage sources and 4 resistors. All the values are given to us. Our job is to use mesh current analysis. So identifying all the meshes in there. How many meshes do we see? 2. Meshes are easy to identify. Closed pathway that doesn't have any other pathway inside it. So there are how many electrical loops? 3. So 3 electrical loops. Some circuits, it's trickier, as we saw with the example, right? There are like 7 or 8 electrical loops in the previous example. But in this case, 3 electrical loops, but only 2 meshes. Doesn't contain any other mesh inside it. So 2 meshes, 2 mesh currents. I'm going to choose both in a clockwise direction. I'm going to call the one on the left as IX. This one is IY. Label this as mesh 1 and the one on the right as mesh 2. So I'm going to begin with drawing out mesh 1. In mesh 1, I have, make this larger. Second voltage source, second resistor, and that's it. Make sure we count the number of components, and then all the components should be accounted for. I have plus minus VA plus minus VB, R1 up top, R2 down below, and I have mesh current IX flowing through the left side, and I have IY flowing on the right. R2 is the shared branch. VB is also shared between mesh 1 and 2, but VB is a voltage source. The value is already given to us, so we don't have to do anything about VB except include in our equation and plug in the values. And that's it. So mesh 1, count the components, VA, R1, VB, R2, all accounted for. How many terms would appear in my equation? How many total terms? 4 components, 4 terms. That's it. So I'll write down the 4 terms, VA, VR1, VB, and VR2 should sum up to 0. Then you apply KVL with the technique you're comfortable with. And let's see if your equation matches up with what I get. Okay. So you have four terms, four voltages, VA, VR1, VB, and VR2. Apply KVL with your techniques. What do we have? We have, now this is me starting from the bottom left corner, going around the loop, minus VA plus VR1. VR1 would be positive, negative this way. R2 is positive, negative that way. This would be positive, negative this way. So plus VR1 plus VB and plus VR2. Do you all have the same equation? Right. So now express each resistor voltage in terms of the mesh current. Again, so these node voltage analysis and mesh current analysis, they are techniques, but again, we generate equations by applying KVL and KCL. You have studied KVL and KCL previously. You have also studied in this course. So the new material, the only new material here is the concept and how to set up the circuit so that you can apply KVL and KCL correctly. And that's the most important. So Ohm's law, I have VA remains as it is. VR1 is not shared. It will simply be IX times R1. VB is a shared branch, but VB is a voltage source, so we don't do anything to it. And VR2, IX is positive, IY is negative. And that's it. That's the equation. Yes. No, we are writing voltages, KV. Oh, for me, what I do is I go clockwise from the bottom left corner, and the polarity I encounter first, meaning for VA, if I'm starting from the bottom left corner, then I encounter minus first. So I put down minus. VR1 would be plus, so plus. VB is plus, so it's plus, and then plus VR2. Again, that is the technique that I am used to, and so I just use that. But again, if you are used to a particular technique, you keep on using that technique. You don't have to do what I do. In the end, the equation will be the same. There won't be any difference with the equation. Okay, so then we plug in all the known values, and in this case, all the known values are VA is 10 volts, so minus 10 plus IX times 5, R1 is given as 5, VB is 9 volts. Now here, I'm going to split it open, so IX times R2 is 10 minus IY times 10 equals to 0. If you have a mesh current in a loop, in a mesh, you count the number of resistors for that current. Those are that many terms and that many constants should appear in your equation. So in this case, I have IX flowing through R1 and R2. I should have two terms with IX in them. 5 times IX and 10 times IX. Okay, if you don't have that, then your equation would be incorrect. So you reduce this and rearrange the terms in the form of AX plus BY equals C equation. And I would obtain 5 times IX plus 10 times IX would give me, what's wrong with this? Okay, 15 times Ix minus 10 times Iy. Minus 10 plus 9 is 1. Minus 1, sorry, and take it on the other side, becomes 1. And I will label this as equation 1. Label that as equation 1. Do you all have the same? Hopefully. Look at the steps. How many steps do we see? Just 3. Write out KVL, then you apply Ohm's law, and then you plug in the values. That's it. 3 steps to arrive at the, well, 4 technically. Yes. Not yes and no. So the question being asked is, why would we choose mesh current analysis? So let's say we are analyzing a random circuit. Okay. It's a random circuit. Doesn't matter whether it has voltage sources or current sources. That certainly is a factor, whether we choose node voltage or mesh current, depending on what we have in the circuit. But the goal is what? We are mathematically trying to solve this. So we're writing mathematical equations. If we want the most efficient method, we want the least number of terms. If we want the least number of terms, we want the least amount of variables. Variables are the node voltages and the mesh currents. So which circuit has the least amount of nodes versus which has the least amount of meshes? If you have 2 meshes, you only have 2 unknown variables. If you count the number of nodes here, 2, 3, 4, 5, 6 nodes. 6 nodes, and if I take the bottom node as my reference, I can eliminate 2. I would still left with 4 unknown variables. If I have 4 unknown variables, that's 4 equations that I would need. So if I was beginning the analysis and I didn't know anything about the circuit, that's how I would approach. How many variables would be required to solve that circuit? That's how you can make a decision between node voltage versus mesh current. In this case, because they're all voltage sources, it'd be harder to write the current expression through each. And so it might be easier to do just mesh current. Yeah. Okay. Make sense? Let's go to mesh 2, where we have IY. How many have MATLAB installed on your smartphones? Nobody? Do you all know how to solve a system of linear equations using MATLAB? Hopefully somebody does. Okay, so I'll show it here for those of you who don't. But again, having it as a tool on your smartphones makes it easier to use it everywhere. So just go ahead and do that. All right, mesh 2, what do we have? We have resistors R2, R3, and R4, and we have VB and VC. Okay, so I'm going to draw it out again here. Then we have VB. And then you have VC on this side. When I say draw the circuit large, I do not mean draw the components and everything as large. Large means just space it out enough so that you have space in there to indicate everything, the resistors, the voltages, the branch currents, everything. So in this case, I'm drawing it very large, but the components are not correspondingly large. So here you have VB, here you have VC on the right, you have R2, we can draw R4 on the other side. And then I have mesh current IY. And on the left, I have mesh current IX. This is plus minus, what is this? R3? Yeah, R3. Okay, plus minus. So 5 components in that loop. So 5 voltages, 5 terms in my equation. If I apply KVL, starting from the bottom left corner, I have VR2. Then I have VB. I have VR3. I have VC. And I have VR4. So resistor voltage will always be positive for me just because I sum up the voltages in the same direction as my mesh current. And so it'll be plus VR2. But for me, my technique, VB would be negative. Okay, VB would be negative plus VR3 plus VC and plus VR4. You apply your technique and see if it matches up with the equation I have. Do you all have the same equation? Okay. Then apply Ohm's law. And I can express R2 in terms of IY and IX. This time we are on the other side. So IY is positive, IX is negative. So I have IY minus IX times R2 minus VB plus VR3 would be IY times R3 plus VC plus IY times R4. Plug in all the known values and then reduce to the form of AX plus BY equal to C. R2 is given as 10 ohms. So it'd be IY times 10 minus IX times 10 minus VB is 9 volts. IY times R3, which is 5, plus VC, which is 1, and R4, which is again 5. All right, let's see. IY flows to 3 resistors, so I should have, let's see, 10 times IY, 5 times IY, and 5 times IY, 3 terms. And IX is only flowing through 1, so 1 term. Reduce the expression, and I would obtain minus 10 times IX plus 20 times IY equals 8. Let's call this equation 2. You solve equation 1 and 2 with any method you're comfortable with. You can solve it manually, plug it into your calculators, use MATLAB, which I will show now. It's not that difficult. You define a variable A with straight brackets, write out the constants from equation 1, which is 15 and minus 10. There should be a space between the two. Then use a semicolon to define the second equation. So minus 10 and then 20 and then press enter. It puts the entered values into a matrix. Okay, it will put it into a matrix. Then you define your results, which not results, sorry, the equation and the constant 1 and 8. And then your answers should be A, that should be, and you press enter, it should give you the two answers. Do you all use, so students who know how to do it, is this the way you do it? Or a little differently? So again, if you have a smartphone, just plug those values in. You have a programmable calculator. I do not have one, so I just solve it manually. Or if it's too complicated, then I would use something like this. You can also use an online solver. There are websites that will do mathematical solutions, solving, automatically online. Okay. To do a manual solve, let's use minus 10 here, plus 20, and I have 15 and 10 up there. So the easiest thing to do would be take equation 1 and multiply it by 2. So I would take equation 1, multiply by 2. That gives me 30 times Ix minus 20 Iy is equal to, what do we have? 1, right? Yeah, 1. So equal to 2. We'll call that equation 3. And then equation 2 plus equation 3 would give me 20 times Ix. Iy is gone. This becomes 10. So Ix is 0.5. Solve this in your calculator or online and let me know if this answer matches up. Yes? And Iy, what is the value of Iy? 0.65, that is correct. And now that you have the answers for both mesh currents, all you have to do is you go to these equations that you wrote out earlier, and you can find the voltage for any resistor, right? VR3 is, that's here, Iy times R3, VR4 is Iy times R4. You take those terms from the equation that you wrote out at the beginning, you plug in the mesh current values in there, and then you have the resistor voltages. At the same time, you also have the answers for the currents that are flowing through the resistors, right? If it's not a shared branch, then the current through that resistor is the mesh current itself. So the current for R3, is simply Iy, which is 0.65. So the resistor current IR3 is the mesh current Iy, because it's not a shared branch. Make sense? Right? So you can find all the resistor voltages, you can find all the resistor currents using this technique. Same with node voltage analysis. All right, questions. Go over the problem. Let me know if you have any questions. Any questions at all? Does it make sense? When you're solving this for when you're solving a circuit that you've never seen before, you ask yourself the same questions that I'm asking now. How many meshes do you see? How many meshes do you see? 2, 3, 4, whatever the answer is. Note it down. Assign mesh currents. Assign the labels. Then draw out each individual mesh. How many terms? How many components in that mesh? Then apply KVL. You should have the same number of terms in your KVL that you have the same number of components. Once you have that KVL expression, then you apply Ohm's law, express each resistor voltage in terms of the mesh current, and then just solve. Again, the technique is not, well, the entire technique is, of the concept is of course new, but the technique that you're applying to generate the equations, that is not new. That is simply KVL. But you need to know how to apply KVL correctly. Okay, that's the most important thing, especially when it's a shared branch. Those are the only two new things. Okay, KVL is something you did before, and you also did it in this class. That's the reason why I had this homework at the beginning of the quarter to refresh everybody's memories about KVL and KCL. It's for this specific purpose. Okay, any questions? Any questions at all? No? You good? Can I have a quiz? Pop-up quiz right now? I see some nods because they know I'm kidding. All right, let's look at what a super mesh is. Again, sounds like a fantastical concept, but it's not. It's simply a shortcut that allows us to eliminate a current source. Similar to node voltage analysis, in mesh current analysis, we may be faced with a situation where we are unable to describe the voltage for that component. That component would be a current source. Okay, if there is a current source in our circuit or in our mesh, we cannot describe the voltage across that current source. So in that case, what we would do is we would take two meshes and we would combine them together. And we create a super mesh. But the application is far more simpler than the actual description. All you're doing is you eliminate the current source, and instead of applying individual KVLs, you apply KVL around those two. That's all you're doing. Okay, you're applying KVL around the outer loop that contains that mesh current, thereby eliminating that current source from your equation. So you combine two meshes together that contain that current source. Yes. That would be different. Remind me at the end when I finish this, I will explain that. The question being asked is if the current source was not shared between two meshes, right? Yeah, that'll be after I finish this. Okay, so if we combine the two meshes, what do I have? I have two resistors, top, one on the left, and then I have a voltage source on the right. And here's the application. Because we are combining both the meshes together, but we still have to account for the individual mesh currents. We do not assume a new mesh current at this point. That would change the entire solution. We don't do that. We still account for the currents we chose at the beginning of our analysis. So this is still I1, and this is still I2. Okay, this is still I1, that one is still I2. Yes. Yes. So the question is, why do we do a super mesh? The answer is, as you stated, because the current source, we cannot describe a voltage drop across that current source. We can assume a variable. We can say, okay, if it's I1, let's call it like, it's 5 amp current source. Let's say the voltage across the current source is like Vx. But then Vx is one more unknown variable in our equation, and we have no way of solving that unknown variable. No, we can't. If we are applying mesh, if you're applying KVL to that first mesh only this one, then we can't. We can do that node voltage. We can write Vx is equal to something, and then we apply KVL to the second mesh, and we write Vx is again equal to something, and then equate both equations, and then thereby eliminating Vx. And so super mesh is a shortcut. Same thing as super node. Super node, you apply KCL at both ends of the voltage source. You eliminate the voltage source from the middle. The same thing here. We are applying KVL in the two individual meshes and equating it together. Rather than doing that, we do a shortcut where we apply KVL in the outer loop. And that's it. This is easier to explain than explaining super node. And super node, it's harder, right? Because you have a node at this end, you have a node at that end. There's a voltage source in the middle. You eliminate the voltage source and you combine both these nodes together. But visually, students and even me occasionally have a hard time writing, KCL if you have like 4 or 5 connections. So it's a little difficult to visualize and then also to explain super node. But mesh, it's easier. You simply apply KVL on the outer loop, eliminate the current source, you take into account both the mesh currents, and you have your KVL expression. And so here, if I just look at the two meshes, the combined meshes, I have 4 terms, 4 components, right? So I have the 1 ohm resistor, I have the 2 ohm resistor, the 4 ohm, and the 10 volt source. That should come out to be 0. What is the current flowing through the 1 ohm resistor? It's just I1. How about the 2 ohm resistor? It's also I1, but look at the top. So it would be I1 minus I3 because it is in a shared branch. And that I intentionally didn't write it out at first because we do have a shared branch, right? So the 2 ohm resistor and the 4 ohm resistor are both in a shared branch. And so it'd be I1 minus I3. Then we get to the 4 ohm resistor, and the 4 ohm resistor, I1 does not flow through the 4 ohm resistor. That is critical. When you apply a KVL expression like this, you keep in mind I1 does not flow through I2. So this would be I2 minus I3 times 4 plus 10 is equal to 0. And that's your KVL expression. You would obtain the exact same expression as was mentioned earlier. If you apply KVL in mesh 1, you apply KVL in mesh 2, and you assign a random variable to the voltage across 5 amps. You would have first half, that's the left half of the expression, and you'd have the right half of the expression. Okay, let's take a pause. You think over that. Let me know if you have any questions. You would only do this if there was a current source in a shared branch. All right. Questions? Does that make sense? Hopefully. I'll take a pause and let you think on that. Any questions at all? Okay, no more questions. Then let's look at what happens if the current source is not shared. If let's say I have a circuit that looks like this. How many meshes? Let's call it IX. Let's call this IY. What do you see? Right at the top, right off the bat. you have IS that is not shared. It belongs to mesh 2, which has mesh current IY. What can we write about the state, the relationship between IY and IS? Do you all agree? IY is the mesh current in 2. IS is the current source in mesh 2. It's not shared. IS, the current source, is not shared with any other mesh. It's just a single branch. So you have IS there, you have IY. I can state that IY is minus IS. And this is one of the cases where I might choose to have my current going in the counterclockwise direction. That would give me a positive value for IS. But you only do that if you can write out the KVL successfully. Okay. So I would still suggest to students, do not do that. Just keep all currents clockwise. And then wherever you see IY with a current source, you simply plug in the Z value. That's it. If the current is in the same direction, then IY is equal to IS. That would be it. Does that make sense to everyone? If the current source is not in a shared branch, you can simply assume, or not assume, conclude that the mesh current in that current source has the value of that current source. The sign would indicate whether it is in the same direction or the opposite direction. If it's in the exact same direction, the value would be positive. It's in the opposite direction, it would be negative. And then wherever that value shows up in IY, wherever IY shows up, you simply plug in that value. You have eliminated one unknown variable from your circuit. You only need one equation to solve for IX. And that's it. One final note. Now that you know that, how can you express this 5 amp source in terms of I1 and I2? Remember, I just stated that if IY is in the same direction as IS, then it's positive. If it's the opposite direction, it's negative. So yes, that would be it. I2 is going up. I1 is coming down. So I can write I2 minus I1 is 5. If the 5 amp was going down, then it would be I1 minus I2 equals to 5. And then when you rearrange the terms, you can express I2 in terms of I1. You can write I2 is 5 plus I1, or you can write I1 is I2 minus 5. And so then you can take those and plug it into one of the equations where I1 or I2 appear, and you can eliminate those. All right, we'll end class here today. I will see you all on Friday when we go superposition. Homework for mesh current is due tomorrow. I will post a document with the hints. There's 3 problems similar to node voltage analysis homework. I'll post some hints. You can look at those and you should be able to solve those problems.